The topic of this video is the inverse normal distribution. So what we were doing yesterday was finding out the area between a given interval. The inverse normal distribution, finds the actual location on the x-axis. So we're looking for an x value as opposed to the area under the graph. So this is the inverse distribution. So for example, a company fills cartons of juice to a normal value of 150 milliliters. 5% of the cartons are rejected for containing too little juice. And so the owner of the company wants to find what the cutoff point is. They already know what the area underneath the curve is. So let's look at some examples. So given that we're looking at the standard normal distribution, we're going to try and find A. So we have the standard normal distribution. Okay. And we're looking at, for the probability that Z is less than A, when that area under the curve is 0.573. So where is that A value? The area to the left, this is equal to 0.573. What is the value that makes that true? So again, we can use our GDC. We approach it the same way. So second VARS gets you to that distribution option. Then you're going to select 3, which gives you the function INV norm, or inverse normal. And then what it looks like on your inverse normal, if you're on an older calculator, when you put in the arguments, you would have the area under the curve, so 0.573, or your answer in a sense. And then you have the parameters for your distribution, in our case, 0 and 1. When you calculate that, you get the answer that A is about 0.184. Let's look at another example. Now we've got the opposite. So the probability that Z is greater than A is 0.3. So now we have the same normal shaped curve. We still have A. Now we're looking at this area is equal to 0.13. Yes, I realize that maybe the areas aren't exactly accurate. What the sketch is just trying to do is give you an idea of what part of the graph that you're looking for, not really the size of the area. Okay. So this one here, now we're looking for 0.3. The inverse normal function only really works when you have less than. So we need to know what the probability of Z is less than A. Now, if you remember, when we first learned about the normal distribution, we know that the area has to add up to 1. That means that the part on the left-hand side of my limit is going to be 0.7. So now, again, I can use my inverse normal on my graphing calculator, the area under the curve, my mean, and then my standard deviation. This is going to tell me that A is approximately 0.524. So we have a less than A, a greater than A. Now we're going to look at one where we've got a left side and a right side. Okay. So here we've got our standard normal distribution again, just like this. We've got minus A, and we've got plus A. So we know that the probability that is in between this part here would be 0.37. But what we need to do is we need to figure out the probability that Z is less than A, because that's the only statement that our inverse normal function is able to work with. So how do we find that out? Well, the probability that Z is less than A is equal to let's do two different colors. It's equal to this green area plus this pink area here. Now, how do we figure out what that pink area is? So if we do 1 minus 0.37, that's going to give us the area on both sides, 0.63. But we know that the distribution is symmetric, so that means the area below minus A and the area above positive A has to be equal. So that means, let's write it this way, each side region is equal to 0.315. So we've got 0.315 here, and this would be 0.315 here. So what we're going to do is take our pink area, 0.315, and we're going to add it to our green area, which is given to us in the question. That way, we have a statement that the probability that Z is less than A is equal to 0.685. Okay, and then we've got probability that Z is less than A is equal to 0.685. Now, only when you have the interval written in this form can you use that inverse normal function, 0.68501. This is going to tell us that A is approximately equal to 0.482. So 3 different examples of where you're finding A, so you're finding the value on the probability curve instead of the area underneath the curve. These examples all deal with the standard normal distribution. However, we are much more likely to be dealing with distributions that are not the standard normal distribution. And so we're going to look at an example for that. So given that we have this normal distribution with, remember this is our mean, and then we've got 3, this is our sigma, our standard deviation. We're going to try and figure out x, where the probability that x is less than x is 0.75. Okay. So let's draw a sketch to sort of visualize the value that we're looking for, like this. Okay. We've got mu is here. Again, not too important where the actual values are. You're just trying to get an idea of what you're looking for. Okay. So we are looking for, we've got x. We know the probability that x is less than x. So on the left-hand side, this part of the graph, the area under the curve is equal to 0.75. So the most efficient way is to use inverse normal right away. We've got our area underneath the curve, our mean, and standard deviation, which is going to tell you that x is equal to 17. We actually got a whole number for this one. You can also standardize. Okay? Sometimes people like to standardize things because it makes it easier to compare data later on. So, or you can standardize x first by shifting to the standard normal distribution. This is a really good exam type question because you're often asked to find something that you don't know. So what we're going to do is we're going to shift our x to a z variable. So our x on our original one is represented just by x. We're going to shift it to our normal distribution, so position represented by z, by taking away the mean and dividing by the standard deviation. So again, this is our formula from yesterday, also in your formula booklets. Then we change our probability statement to be in terms of z instead of x. So we've got probability that z is less than x minus 15 over 3 is equal to 0.75. So when we do inverse normal, using the standard parameters, we would put in 0.75, 0, and 1. This is going to tell us that this answer here, so it's not just a variable anymore, we've got x minus 15 over 3 is equal to 0.6745. Now we are solving for x in this case. Okay, and you will get about 17. So standardizing, not really that much more efficient here. In future problems and more challenging problems where you don't know the standard deviation, but you do know the x value, you can use this approach to be able to solve for other missing parameters. So let's look at one more example. This is the example from the statement at the beginning. Cartons of juice are such that their volumes are normally distributed with a mean of 150 milliliters and a standard deviation of 5 milliliters. 5% of the cartons are rejected for containing too little juice. That would be disappointing. Find the minimum volume to the nearest milliliter. Also important, tells you what to do with your answer, that a carton must contain if it is to be accepted. So I'm going to draw standard normal distribution. Okay, I've got my mean here. And I'm going to define some variables since I'm working with a word problem. So let's let V represent the volume of a carton. And let's let M represent the minimum volume. So then I can write my normal distribution, V, as a normal distribution with defining parameters 150 and 5. And then my probability statement is what's the probability that a volume is less than my desired value of M. And I want to know what that value of M is when the area underneath the curve is equal to 0.05. Okay, 5% is the area under the curve. That's your distribution amount. Area under the curve is always translated into a decimal. Once we've set up this statement, now we can use our inverse normal function on our graphing calculator and input our parameters. And this is going to tell us that the minimum volume that a carton must be to be accepted would be 142 milliliters. Otherwise, it's in that 5% of cartons that are rejected for containing too little juice. So the inverse normal, really cool application of the normal function, working backwards to find the point on the normal distribution curve as opposed to the area underneath the curve.